Hi folks, my name is Nathaniel. Currently managing the team at Healthy.io, where we're turning smartphone cameras into clinically, medically approved devices. And I think how many people here are working in the computer vision field or are familiar with it? Okay, cool. So I think anyone who's worked in vision, and this is relevant to everything else, but you're probably not only doing deep learning, you're probably also doing some classical vision. And hyperparameter optimization is not only about hyperparameters for deep learning, it's also about hyperparameters in general. It could be how much you weigh your classical algorithm versus your deep learning algorithm. It could be merging the two in some way. And of course, it is also in complex deep learning models, you no longer have only your learning rate, you have your momentum, you may have all kinds of other parameters, say weightings of different losses, and the number of hyperparameters becomes quite large. And what we'll talk about today is not a specific method, but rather a generic class of methods, which can be useful also for hyperparameter optimization, but not only. It's a generic machine learning optimization method, which can be used for classification problems and a lot of other interesting things, especially if you guys don't have a lot of data. Bayesian optimization and Gaussian processes are one of the ways to go. And today we'll talk, in the very short time we have, try and kind of give a whole semester overview of the topic. But if you guys, at the end of this talk, understand, give or take, what Gaussian process is, understand the basic idea behind Bayesian optimization, I think I'll be pleased. So it's a short time. Please ask questions during the talk, unless they're very long ones, which in that case, feel free to reach out afterwards. So without further ado, I'll start with this problem. So we have a bunch of points, and we want to solve a regression problem, right? We want to solve the function to go through all the points. We go through them in a deep learning space. You may have sampled your deep learning network at a bunch of different hyperparameter points, and you want to understand what the function looks like. You want to know what it looks like so that you can find the best next minima or optima in this case. And this is, in general, a very hard problem. If even this one simple one-dimensional problem, I don't think anyone can write a function that will fit this, an explicit function, explicit model. And even if we could, this explicit model may have hundreds of parameters in the one-dimensional case. In an n-dimensional case, it could be millions. And if only we could do regression-based predictions, as I understand, given a bunch of data, what's going to be the next best point, or what's going to be the value at a certain x value. If only we could do it without an explicit model. We have a black box, like a neural network. We put in hyperparameters, we train, we get an output. It's a black box model. We don't know anything about it. And the question is, how do we do regression with a black box model? And this is what we're talking about today. So how many people are familiar with that formula up there? Great. OK, so we've come to the right place. I won't go on about this a long time. But to remember what Bayesian inference does is we have some data, x. We have some parameters, theta. And what we want to find is a posterior, right? We are given some prior over what the probability is of the various parameters, p of theta. We have the likelihood, and we want to know what the posterior distribution is. And in regular Bayesian inference, theta may be a space of parameters, x is your data, and now you get, you're getting p of theta, so you get a probability over some number, right? You have a probability distribution. It's a function of a single variable, say, or a multivariable, but still a probability over numbers. That's something I think we're all familiar with from statistics course. A probability distribution over numbers. I'll just say one thing about Gaussian processes in general. Gaussians are what they're called conjugate priors, which means if you put Gaussian in the prior, you get Gaussian posterior, which is a really nice effect, which we'll utilize shortly. So Gaussian process is really, I think, a beautiful mathematical idea. It's saying instead of thinking of a prior over all the possible numbers, we'll think of a prior over all the possible functions. And what that means is, if we look over here, what we want to find is the most likely function, not the most likely value. We have all the functions in the world that could fit this model, and we want to find what's the most likely function. So it's kind of a switch of thinking of probability distributions over numbers to probability distributions over the space of all functions. So in essence, that's what Gaussian process is. And assuming that we can even think of this kind of weird mathematical object, which is a probability over functions, then in theory we can say, OK, let's take a prior. Say, I don't know what the function I want to fit. Maybe it's, a flat line. That's my prior. I don't know anything about it. And we'll stick in the data we got from our deep neural network, say what the loss is at each hyperparameter point. We'll get a bunch of data points, and we'll compute the posterior. And once we have a posterior, the posterior will tell us what that function now looks like. So it's not a function now, it's which functions are most probable to fit the data. That makes sense so far? Okay. So this lends itself really nicely to regression, not only to regression, and you guys can look up afterwards different models are used for it, but regression is really nice because what we're looking for is a function, and this gives us the probability of a function being the right function. And of course, we can just choose, the most probable function, and that's the function we want to use. So I promise it's the most mathematical slide, so if you pass this one, we're fine going forward. So basically the idea here is, this is the definition of a Gaussian process, but what this tells us is, if you choose a bunch of points x, and you have a bunch of function values f, then the joint distribution is Gaussian. It's a multivariate Gaussian, and what that means is that if you have, let's say, 10 points that you calculate a loss for, and we'll see this in a second, it gets a bit less complex than that, all these points are jointly distributed. So if you...
What about the noise in the sampling?
The noise? I'll get to that in a second. So 2 slides from here, I think, or if not 3. So they're all correlated. So if you have 10 points, let's say you ran your neural network with 10 different sets of hyperparameters. Each set of hyperparameters is some sort of x. F is the final loss that you got. What this tells us is that these function values are correlated with each other. How are they correlated? With the Gaussian function, and we'll see what this means. And one thing to note before we go further is an ordinary Gaussian distribution has some sort of mu, the average, and a covariance matrix, and these in general are not a function of your data, right? When you fit a Gaussian model to data, you have data, and then you get some numbers. In this case, what we're going to see is that the covariance matrix and the mean vector actually depend on the data, and we'll see how it looks in a second. So we talked about this, a Gaussian process is basically a distribution over functions. So if you sample a probability distribution, what do you get? You get a number, right? If I sample a number from, let's say, a multi-bit varied Gaussian, I get wherever the dimension of the Gaussian is numbers. When I sample a Gaussian process, what do I get? A function. So these are examples of functions which we sampled from the Gaussian process. And what we see here is 2 very different graphs, right? The functions over here are kind of smooth. These are kind of really noisy. And the difference between them is the covariance matrix that we saw here. So basically, what this covariance matrix tells us is how are these points correlated. So if you have a bunch of x's that are really close together, and the covariance is really large, what that tells us is that if the values are really large, it means the f values at these points can be very different. It means there's a lot of covariance. So there's not really a lot of dependence between different values. If we have a small covariance, it means that everything has to be really smooth, because points that are similar have to kind of cluster together, because the covariance can't be very large.
What is the basis of the function space you're sampling from? I mean,
how do you choose the basis of?
Yeah. I mean, how do you define the space that you're sampling from that Gaussian distribution?
So you can do a bunch of stuff, but in this particular one, you see the gray bars over here. That's the prior I used to generate these. And the prior is simply say constant function is 0 with some Gaussian noise. So it's just saying, okay, I don't know anything. It's around 0, and that's all I know. And of course, if you get more and more data, then it will support your posterior that the function should be somewhere else. So again, so the idea here that we're trying to use is saying we have a kernel which depends on the data, and that kernel tells us how much close function values should be correlated. So if we have 2 function values which are very close, the k at these 2 points will tell us how much covariance or how much we allow these 2 points to differ. And so someone who asked about noise previously, in reality, how do we, we'll have some noise, but we can use different models for our k. So we have a k which is a covariance matrix, and what we want to do is use some sort of model which tells us, given 2 points, how near or far, how large the covariance can be. So I just want to use one simple one, which is the first one right here. This tells us that if you have 2 points with some sort of length scale, it exponentially drops. So if I have two nearby points, I say they have to be really close together. So if I measured the function value at one point, the point next to it is probably not going to change a lot. But if I measure something really far away, it exponentially drops to 0. There's no effect, and it doesn't tell me anything. I have a lot of variance in that point. And you can, of course, add very complex models. You can make squared exponential model with noise. We'll add some sort of noise over here saying even though I measured the point, I can still allow for noise. In, say, a neural network type of case, there's no noise. Because the hyperparameters you measured, you actually got a certain loss. Maybe that's your actual value. Maybe you assume there's no noise involved. In, say, if you did a measuring case, maybe a linear regression problem, you have a machine or some sort of something with noise in it that outputs values, you can assume that there's noise. Some interesting things people do, for instance, use a sine function or any sort of periodic function. If you know your data is periodic, you can model it that way. So basically, the kernel function that you use is your choice, and people have used various different kernel functions for different problems. And it's basically just a way of modeling your data, but you're not modeling the function. You're just saying, what's the connection between two nearby points, roughly? You're not specifying any specific function. So even in Gaussian processes, we still have hyperparameters. We have these L's, we have these sigmas. So we had a problem of optimizing hyperparameters, and we got to the same problem of optimizing hyperparameters for hyperparameter optimization. So what do we do with that? So we'll talk about how we optimize hyperparameters in a second, but before we do that, what's the general process? So we start with some prior, and the prior again can be something really simple. Say the loss for your network is always equal, no matter what the hyperparameters are. It's always the same. That could be your prior. It's your choice, and it doesn't really matter much, because once you start getting in data, that prior is going to be forgotten pretty quickly. You start with some Gaussian process, and then you have some new points that you want to predict the values for. So we had a bunch of data points that we sampled, say with certain hyperparameters. And then we have new points that we want to check what's the value going to be at that point without actually running and training the network again. So if we have some new point, we have a prior, we have a posterior, we can calculate now what's the most likely functions again. And I'll just say one note about this is a really expensive operation. It involves inverting a matrix. So if you had, how many hyperparameters do you generally go through when you train a network? Like sets, probably a couple of tens at least, right? So this involves inverting the matrix of a couple of tens of points, and that can get very, very expensive if you have lots of evaluations, which is why this method is used for things where you don't have a lot of points, give or take. Questions so far? Okay. So if you feel lost, I hope this slide will kind of help put back the intuition. So in all these graphs, what we have is a bunch of points. And what matters here is these hyperparameters in the Gaussian process. And what you see here is here we have 5 points. And you have a very small length scale, which basically means points that aren't near any other point. The covariance can be huge. And what you actually see, the gray bars are the posterior. And the functions, the colored lines, are functions that we sampled from that posterior distribution. So if we go back a couple of slides, these were a uniform prior, where we just assumed the prior was flat. And here is a posterior of what we actually sampled 5 points and what the posterior looks like. So basically it says, if we have 5 points, we know exactly where they are. There's no noise involved. All the functions have to go through these points. So all these functions are ones that we sampled from our posterior. And you see that they indeed go through the points. And you see that when we're far away from points we sampled, we have a lot of variance. What happens if we start increasing the points? Once we increase the points, then near the points we sampled, there's of course not a lot of variance. And outside the points we sampled, there's still a lot of variance. What happens if we change hyperparameters? So if we allow the length scale to be larger, then what you see here is that the functions get kind of smoother. Each point has a lot of sphere of influence. The length scale is larger, and points influence farther away points. So what these 4 graphs show is basically how the Gaussian process, the posterior that we get, the functions that are likely to fit the data, progress. As we have more data, and as we change the hyperparameter of the Gaussian process. Yes?
The difference between the top and the bottom?
The difference in the top and the bottom is basically the length scale. So if you go back, this is your kernel function, and this is the L involved. And basically what the L tells us is how fast the exponent falls down. We're fine. Okay. Okay, so now in theory, we don't need any models. Linear regression is thrown out the window, right? We just have points, and we can regress any data we want to any model. We don't need to explicitly provide it. Everything's perfect, right? So it's never that easy. So we still need to determine the kernel hyperparameters to determine the original hyperparameters, which is one problem. And how many are familiar with the term Bayesian model selection? Okay, half. So check it out. It's an interesting topic on how to choose your best model in machine learning. But I'll say in very, very brief, basically, if you have, say you had a bunch of points and you want to fit a polynomial to a bunch of points, right? If you have, let's say, 100 points, you're not going to fit a degree 100 polynomial, even though it's going to go through all the points. Why? Because your average 100-degree polynomial is unlikely to create the data that you specifically observed, right? If you just randomly create a model with 100 parameters, it's not going to create your data. And vice versa. If you have 100 points and distribute something like a really complex function, probably a linear regression, a straight line, is not going to fit them very well either. So you have a balance between models that fit your data really well and models that don't fit the data at all. And you want to be somewhere in the middle, right? We want the Goldilocks kind of parameters are just right, not too warm, not too cold. So what we try to do in Bayesian model selection is say maximize the evidence. We have data given the model, and we ask, what's the highest evidence? What data can give us the best model? We do the same thing in Gaussian process. So we have these hyperparameters for the model, and we ask, what hyperparameters are most likely to give us the data that we actually observed? And I'll show this in the graph. Anyone who wants to learn a bit more about the topic, this is probably the canonical work on the topic. And the graphs that you can see on the right and the left and the bottom, the black points are actually the same in both of the graphs. So this may not look the same, but all the black crosses are actually in the same positions exactly. And of course, you can fit a very simple smooth function, and you can fit a very complex, wavy function, and both fit. And what you can see here is these are two hyperparameters for the Gaussian process, and we have local minima that give these two solutions. So I'm not going to go into how this is calculated, but basically, for any given data, we have a method of calculating what the best hyperparameters are for the Gaussian process. And once we find them, there may be local minima, but assuming there aren't, we now have our best model. So if we go back to this question, the answer is, yeah, give or take. We have a bunch of points. We find the best hyperparameters for the Gaussian process. And now we have a Gaussian process that gives us the probability of the best function that fits that data, which is completely implicit. There's nothing in there that says what the function is. It's just a generic distribution over the space of all possible functions that fit our data. So that's Gaussian processes, I think probably one of the shortest explanations on it. I hope I haven't lost you yet. And it's a really interesting field. It's still an active research field everywhere in machine learning. Once you have a regression model, it's very easy to turn into classification model. You just say, I have all the dogs have to be +1 and all the cats have to be -1, and you fit a regression problem to that. So you can really categorize any classification problem as a regression model and solve it this way. There's very interesting applications in clustering. So if you do semi-supervised or supervised clustering, because the Gaussian process kind of finds the underlying distribution of the functions, this is very good for clustering, because clustering, what you really want to find out, you have a bunch of, or semi-supervised clustering, you have a bunch of points that you sampled and have labels for, and most of the points you don't. So how do you use the points that don't have any labels to learn the distribution? These are works, again, that are being published all the time, and it's a really active research field. And in deep neural networks, it was mentioned previously that a single layer neural network can describe really any function. And one of the ways of proving it mathematically is that you can model deep neural networks as Gaussian processes. And it's, again, an active research field trying to use Gaussian processes to model deep neural networks and understand the more theoretical properties of them. Those are familiar of Uri and Gell's work on dropout, and Bayesian neural networks also use this. Very interesting field, and again, in the interest of time, we kind of made this very short. Questions so far? Yes?
So how do I use that to find my neural net, my favorite neural net?
Excellent question. So it's next slide, of course. I'll just say, for those who have lost the mathematical details, I promise one last slide in the very practical take-home application that you can take. So stay patient. So Bayesian optimization. So once we have a Gaussian process, now the question is, okay, how do I find my neural network's best hyperparameters, right? And so here's the task. The task is we want to find the global minima of some unknown function. In this case, it's the loss of a neural network, given only evaluations. It's a black box. We evaluate once with certain hyperparameters. We train. We get a certain loss. Do it again and again and again. And what we really want to find is the best set of hyperparameters to choose next, correct? And if we model our data with the Gaussian process regression, what we basically get from this, we get a probability distribution for the y value at every point x. So what that tells us is, say you took a bunch of hyperparameters, you trained your network, now you have a new set of hyperparameters you want to test, you can get the probability that your loss is now going to be lower or higher than it was previously. So one example of a loss, it's not the loss you can have, but one example, say your current loss is some eta value, that's the lowest value you got, and you want to evaluate what's the loss for your next best choice, right? So what you can say is, if my loss decreases, then I choose that value as my loss. And if my value didn't decrease, I just leave it as is. This is just a very, very simple loss function for defining what the next best point is, right? So this is really, really simple, saying, if I improve, I'm going to take my improved value. If I don't improve, I'm staying flat. That's the loss function. So if I have a loss function, I can optimize over a loss function. And the loss function, again, is only to find the best x's, the best hyperparameters. So what I'm trying to do now is finding the best hyperparameters so that my network loss will be the lowest. And this is one example of a loss. But once we have loss functions, and we have a prior, or a posterior in this case rather, this gives us the probability distribution over all the hyperparameters in my model. And this gives me the loss of my neural network. So if I can solve this integral, this basically tells me what the expected loss at any point is. So if you say, I want to decrease my learning rate, this will be able to calculate for you what your expected loss is going to be. And you can say, okay, what's my next best step? Let's choose the one with the smallest expected loss. And keep on doing that until you find the best point. So I have a graph here from a paper on this topic. And what we see here is the following. You have an observation, which are these little crosses right here. You see 1, 2, 3. You have the mean, the red line, and the pink area is your Gaussian process. It's a posterior. That's a distribution over all the functions that fit your data. And the y is the loss, and your x is your hyperparameters. And in this case, it's a very simple hyperparameter. I don't even remember what they're using in the paper, but bear with me for a second. So what they start with a single evaluation. The single evaluation, what does it tell us? It tells us that the function has to go through this point, but everywhere else I have absolutely no idea what happens, right? And what you can do is you can calculate the expected loss. And once you calculate the expected loss, you can find what the nearest point is, the lowest point, and do another evaluation over there. So we had first evaluation right here, second evaluation right there, and then third one right there. And this process very quickly converges to a global optima. So within 1, 2, 3, 4, 5, 7, it's kind of difficult to see the crosses right there. You can converge very quickly to not necessarily the global minima, but a very good local minima for your hyperparameters. And I think this number is a lot smaller than most of us have tried. If anyone here is still using grid search, please don't. But still, even with random methods, you probably run through more than 7 or so evaluations before you choose your right set of hyperparameters. Questions? Okay.
How
How you got from the 5 to the 7?
So it just is skipping. They're not showing all the images, but basically,
How you escape the local and get to the global?
because what you're doing is you're not taking you have all the functions that your Gaussian posterior gives you, and you don't take the lowest point of that function. What you do is you take the lowest point of your expected loss. And your expected loss is a dark blue line right here. So in this case, this is your expected loss function, and you look at what's your expected, this is a Gaussian process of your loss, and this is the expected loss. And you see this point happens to be the lowest point in the expected loss, so you choose that one next. And then once you chose that point, that's that point over there, and then it goes on, so on and so forth. And what you can see really happening is here, in this area, we used to have a lot of covariance, right? We didn't know what the value was going to be. And once we sampled it, now the covariance in that area becomes very small. We know exactly what's going to happen if we choose these hyperparameters, and probably what's going to happen if we choose hyperparameters that are fairly close nearby. Okay, so this is, in theory, this works. Now, the problem is what loss function you choose, which are known as acquisition functions in the literature. And this relates, again, to the previous talk, this idea of exploitation versus exploration. Any global optimization problem, you have this problem, which is I'm already in some local minima. I want to exploit the knowledge I have, or I don't know where to look, and I want to find new points, explore new values I haven't looked for. And you have this problem all the time, and hyperparameter optimization is just one example of that. And what people tend to do, this is, for instance, one common loss function. It tells us it balances between the mu, which is the average of the Gaussian process. It says the Gaussian process thinks where the loss is going to be. So if I just minimize this, this is going to be great. That's exploitation, saying use the places where I already know I'm in a low value. Or I can take exploitation. I can take values where the kernel is really large. And when the kernel is really large, it means I have absolutely no idea what the function is going to do in those places, and maybe kind of search around in those for a while. So there's various acquisition functions. None of them are optimal, and every one of them kind of balances out between these two competing factors, exploitation, exploration, and you'll see the theme repeat itself really in any optimization problem you read about. So different loss functions lead to different balances, and anyone who's kind of reads about in the field will see these loss functions. But at least when you come to this talk, you'll remember that acquisition function is what you should look for, and then you'll know what to read. So this one is a paper that was accepted, I think, maybe accepted in NIPS 19. And what you see here is a hyperparameter optimization using Bayesian optimization for CFAR 100 and VGG benchmark. It's not the largest network out there, but it's not a tiny network either. It's not AlexNet on CFAR 10. And what you see over here, this is the min function value that they got. And this is how many minutes of training, or how many hours of training. And you can see a number of interesting things. The dotted gray line up here, this one is just random. They didn't even mention grid search. I don't know how high up there it is. But even random, you can do a lot better than just randomly choosing hyperparameters. So all the ones that start with GP over here are all Gaussian process Bayesian optimization methods. The paper specifically showed a new method called deep Bayesian optimization, which tried to factor out various competing effects, and you guys go read the paper. But I think what's interesting from this graph is even, okay, the state of the art is amazing, but your generic Gaussian process does so much better than random, converges the network so much faster, just no reason why not to use it. So I promised you guys the last slide. PyTorch, about a half a year ago, released a framework called Axe. And seriously, these I don't know if you want to call it a single line or 4 lines of code, but that's all you need to optimize using Bayesian optimization for your hyperparameter tuning. You can throw in any black box you want into Axe. This is just your function, train, evaluate, returns your loss. In this case, it's just learning rate, momentum, and it will find the optimal hyperparameters for you. It's really a no-brainer, and you can use it for a bunch of stuff other than neural networks. You can, of course, use it for classical problems or any other optimization problem you have. It's really a great no-brainer tool, and I think it has some defaults. It's probably, you don't see any mention over here of acquisition functions. There's no question of how to do hyperparameter optimization for the Gaussian process itself. There's a lot of things hiding underneath the hood, and AXE is really a very thin wrapper around what's called BowTorch, which is, again, Python's a PyTorch-based BO framework. So anyone who's interested in a research aspect and wants to look into various functions and so on, BowTorch is a very, very powerful tool. But for those who don't and just want to take one takeaway home message, go ahead, use AXE. You'll get much faster convergence in your neural networks with really, really not a lot of effort. So that's all from us. Any other questions? Go ahead.
Okay, so when you measure the loss function, right? So probably the minimum, you're doing your realization of your hyperparameter, right? So you have this measurement of your loss. So it still have deviations, right? It's not the exact number. So I'm saying that. So you basically you're localizing your Gaussian process at some point, right? But it still has a deviation.
Yeah. So the question to those who didn't hear was, even when we train a neural network, our loss still has some noise because we never train it fully to the global optimum. And each time there's a noise. I think I showed earlier, but you can see over here. It really depends on your kernel function. There are kernel functions that allow for noise, right here. So instead of forcing all the functions to go exactly through the points, you allow them some noise. So the functions no longer go exactly through the points that you sampled. They go with some noise. And again, AXE will give you some sort of optimization, and you can dive deeper and try to play around with the parameters. If you already know that, say, maybe you don't want to train 100 epochs, maybe you just want to train 10 and increase the noise, or something like that, go right ahead. It's an experiment that you can do. Yes?
So you were mentioning it. So do you have any experience with Bayesian neural networks, with the Gaussian work, and maybe this mental garment, I think is it?
Yeah.
Did they give you uncertainties? This is wonderful, but do they work?
That's an interesting question. I mean, there's a bunch of competing works out, and it's an active field of research.
Do you have any experience with it?
Not enough to tell you whether they work. People have reported different things, and there's some new papers out there as well on that topic. Some now from ICCV this year. Any other questions? Sure.
Can you use Bayesian optimization for any type of development as a loss function? It doesn't have to be only deep learning.
Yeah, exactly. So
it's my own model that I developed, and it has some loss function.
yeah, so again, in this function, you just put some sort of Python function that returns some number, and it will optimize it for you. I'll just say, in Healthy I/O, we're doing a lot of stuff with classical computer vision that has to run very quickly on device, and so some stuff that you may not have enough data for, or just no reason to run deep neural networks. And in those cases, you may have a lot of kind of magic numbers floating around your vision code, and you ask, okay, let's go through all my data. I have 100,000 samples. What are the best hyperparameters I can choose? And they're not deep neural network in any way. They're just random magic numbers that are in your vision code, right? That you can, instead of saying, oh, look, some sample, let's choose over a large hyperparameter space and choose the best ones. It's a generic framework for optimizing black box problems. Hyperparameters and deep neural networks is just one example. Yes? Okay.
Just a small information. If you have, for instance, a supervised model, and you have created your own metric of how to estimate the goodness of fit, you can use this optimization as well.
Sure.
If you create a loss function.
Yeah, use any optimization problem. Yeah.
Because of the heavy, so like enter the 3. So does this limit the number of hyperparameters to tune, or is it?
It primarily limits the number of evaluations that you can do.
Sorry?
It limits the number of evaluations that you can do and the number of hyperparameters, but more importantly, the number of evaluations that you can do. That kind of relates, but the n third is the number of evaluations, and then the problem becomes that when you have a large number of parameters, to find the best optima, because of the curse of dimensionality, you need a lot of evaluations. So the problem really isn't evaluations, but yes, if you had like 100 hyperparameters to find, this is not going to work. Yeah.
But so is it also a function of how big is your data, or just the
No, it's not a function of how big your data is, and what's nice about it, it's a black box model. So again, you can have every iteration of your deep neural network could be 3 days of training, and that's just one point. And the Gaussian process doesn't care. It cares if you start having, if you had 100 million evaluations, this is a no-brainer. But the black box model, you don't care how long it runs for.
How it's compared with interop or tune this?
I'm not familiar. Maybe we can talk afterwards. I don't know what the base technology is underneath this.
Regarding this acquisition function,
Yeah.
it looks like it's an important part. And what's the current, I don't know, state of the field regarding this acquisition function? Because everybody talks like this is very generic, but after all, you have like only 3 of them implemented in this, how to call it?
So I think the upper confidence bound method, which is this, is fairly standard. It's still, you need to evaluate 1 extra parameter over here. And again, there's various ones. Well, I think what's nice about the method is it generally works, even if you find the best one. The DPO guys did a lot of work on fine-tuning the exact acquisition functions and when to use them, and they did a lot of work on really fine-tuning this. But even without all that, and they got amazing results, but even without that, it's still, fairly free lunch.
DPO, like they use their own acquisition, deep network-based acquisition function?
No, it's not actually deep, but they tune the acquisition functions and when to use them and how to choose them specifically for deep neural networks. So it's not a deep neural network acquisition function, it's basically a bunch of heuristics on how to apply it for deep neural networks.
So right now it's not like too much choice for us, like a layman.
Yeah, so I think again, if you're a layman, you don't know anything, just like plug and play, it works. And if you have specific problems you want to solve, then you can go and dive deeper, of course, into literature, and there's a lot more than what's covered by a half-hour talk. So, last questions? Okay, folks, thank you so much.